So it's recorded. So get ready. One.
Yes, sir. Whenever you're ready.
Okay, so I will make you co-host.
Okay. I'll try to share my screen. All right. Can you see my screen?
Yeah. Yeah, let me see if I okay, that should be okay then. All right. So yep. Let me push the start. So you got a 15 minutes. I'll remind you a few minutes after. Okay, go ahead. Introduce yourself and
All right. Hey everyone. I'm Juan.
oh,
So
one this is EV charging system. Oh, okay. This is for renewable, right? Okay, all right.
yeah, they're
Go
both
ahead. Yep.
sort of. Yes. So our project was or is on simulating a solar powered EV charging station with energy storage. I missed that part on there. So the purpose of the project is to utilize a photovoltaic system with energy storage, but in the context of distributed generation. The reason we are only simulating one file is because it would be too heavy to simulate many iterations. However, even though the system should be able to just charge its batteries and charge a PV without being grid connected, it should be grid connected because it can provide generation for the grid. It can provide energy storage for high demand when it's necessary, and it can also serve as a power sink when necessary in case it's some type of generation that cannot really lower its output. So this works in synergy with being an EV charging station, first because it can charge an EV at nighttime. So that would be with the grid if it's needed, or with the batteries, ideally. And also in maybe not remote, but less populated areas, this was also the motivation for the project in the first place. So giving additional purposes to the charging station would make it maybe a bit more attractive for people to build them, and hence it would be easier for people to adopt EV, just like it's easier to have a car if you have gas stations nearby. And also in the context of a smart grid, if assuming the EV is capable of bidirectional power transfer, the EV can also provide some of its energy, assuming the owner is willing to do so. So the whole project was on using PSCAD simulation, mostly because PSCAD is very good at providing documentation and examples. So it's easier to figure things out. So we started off from two files. The first one is the actual grid connected PV model. So
it doesn't move, looks like, are you in presenting mode?
yeah, you can see. Or,
I can only see the cover page.
oh, what about now?
Okay, yeah. Okay, now I can see.
Okay, maybe we'll have to do it like this if it's okay.
Yeah.
All right. Well, yeah, the other slides, there's not really much to show graphically. So, what was that? Okay, so the grid connected PV system model. So, as you can see, it has irradiation and temperature control this is the solar array. It is connected to a boost converter. Then the high side then connects to a voltage source converter. And I'll go over the rest in a bit. So the boost converter is controlled by a maximum power point tracker that it provides a reference for both the boost converter and the voltage source converter, depending on the output power of the solar array, which depends on its irradiation and temperature. The second file is a battery charger model. This is the original one that I started to work with earlier in the semester, which is not exactly the one that we ended up using because everything that you can see to the left side didn't work very well because it was originally built for PSCAD version 4. So it had to do some weird conversions in order to work with the newer PSCAD, and you needed an additional DQ axis converter file, so it would just take forever to load. So we're only going to focus on the right side, on the charger and the battery itself. The newer battery system that we ended up using is mostly the same, but it has a 500 volt battery bank model, which is a bit more sophisticated, and it has a state of charge signal output. And well, this is not really a difference, but both are controlled by, or the charger is a buck boost converter that charges or discharges the battery depending on its mode. And I'd like to point out that this battery is not supposed, this is supposed to be the battery of the station, not the battery of the car. And well, I'll elaborate on that a bit later. Oh, right, and so the battery system is connected to the PV system in between the boost converter and the voltage source converter, as you can see here. And oh, okay, so this is to the right of the voltage source converter. So it has an adjustable load, and it also has a synchronous generator, a 100 MVA synchronous generator that it represents the rest of the grid. So if we have negative power flow, that just means that the system is supplying or delivering power to the grid in spite of the load. So this is not supposed to be like an actual generator. Okay, so moving on to the performance. At default settings, it has a 0.2 megawatt and 0.05 MBAR load that is adjustable. All of the simulations were run as just 28 degrees Celsius, and for this first one, 800 watts per meter square irradiation. So this is the battery operation at default during charging. As you can see, the rate of charge slows down a bit after the first couple of seconds, and also the battery voltage stabilizes. So under these circumstances, the PV is producing enough power to meet the load and also to still provide about 20 kilowatts to the grid, which is why we have negative power flow. And during this charge operation, it dropped about 15% during the 50 seconds in PSCAD time, 50 seconds. And during this, oh, sorry. Right, and during this operation, it's more of the same, but it can deliver additional power to the grid just because the battery is discharging as well. Now, mid simulation, if you switch from charging to discharging, you can see how the power going through the voltage source converter increases, and well, the power to the grid just it goes more negative, but that just means that more power is being delivered to the grid. Okay, let us speed up. So first at reduce irradiation 300 watts per meter squared. So the battery is charging at a rate of about 20 kilowatts. And as you can see, the SGen power is no longer negative. That means that the system is actually relying on the grid to meet the load, and it's not quite meeting the load, really. Then during charging operation, we just set the load to half just to see what the impact would be. So it's not very different other than it's charging the battery. It's charging at a relatively slow rate compared to discharging, but this was due to the current limit that the charger has. So changing that would break more or less a simulation. So we didn't experiment a lot with that. Oh, okay. So yeah, the charge operation, and finally night operation, which is at zero irradiation, it's not very different. It's just the battery and the grid operating without the PV at all. Though we would get some strange power readings from the PV that didn't make sense, which is why we left it out of it. So conclusions and difficulties for the project. So as I said before, originally there was supposed to be a second battery charger that was supposed to be connected to the same DC bus as the first battery charger that would represent the car. But since that battery charger in the file was not like a library or a definition, but just an element, if you try to duplicate it, then it would not be another iteration, but just the same thing with the same signal names, and it would they would not interact well with each other, so it would complicate things too much. So I just left it at that. So I think the system is capable of fulfilling its job as energy storage and generation while being an EV charger. And also, ideally, we will have like many smaller versions of this that would be charging many cars and operating in conjunction. But already simulating just one iteration of this, like it was like 50 seconds PSCAT time, but it would take like 10 minutes on real time. So even a second iteration would be too much, and PSCAT is not really appropriate for that. PSLF would probably be better, I think. So that's about it. Any questions?
Any questions or additional comments from members, team members? Okay, if not, I have questions about this. What is the takeaway from your project here?
The takeaway.
Yeah, what do you gain? What do you learn? What to do, what not to do, kind of things.
Well, on the first place, I think it's so in order for like microgrids, or not microgrids, but smart grids and EV aggregation to be adopted, I think there has to be an incentive first for companies to want to do that. And on how the project itself went, well, let's just say things can, if you make the project even just a tiny bit larger, it can get a lot more difficult. Like just adding a second charger would jump the difficulty of the project too much, which is why it seems to be a bit disconnected from it being an EV charger. But
so what about the software you mentioned about? Have you considered like MATLAB Simulink, Simscape?
I think that would be more useful in a simulation of like the EV itself, right?
Yeah, and you sort of like consider state of charge, and your observation is on minutes, right? And it's like it takes too much time for you to use PSCAT.
Yes, yes.
Yeah.
The more you add to a file, it really ramps up the waiting time for the simulation to finish. It was not excessively long, but it certainly didn't take twice as long as the files themselves. It was like maybe 4 times or 5 times. So yeah, maybe some PSCAD is great because of all the documentation, and they provide the resources to learn not only about the simulation but also the concepts behind the simulation. But if it gets too big, it just takes too much time,
Yeah, you
which is
said
why I think
15.
PSLF would be better to
So
have
so how long does it take for you to run the simulation, one cycle?
like 8 to 10 minutes.
8 to 10 minutes. Okay.
Of
So
course,
where did you? Is it in computer lab?
no, that's on my own computer.
Oh, your own computer. Okay.
Yeah,
Okay. All
I don't
right.
know if that's, yeah, it might be my computer, but But yeah, it just takes a long while.
Okay. So, all right. So if there is no more questions, we need to move on to the next one. I believe that's, is that Bruce?
Yeah, it's me.
Thank you.
Can you
Okay.
hear me?
Yeah, yeah. So
Okay.
Stop
I
the
think you
share
need
then.
to stop sharing.
Okay, let me try to share screen. Okay, it says host disabled participant sharing screen sharing.
Yeah. Oh, I see. Okay, hold on. So I have to make yours BE, right? So I have to make you
Yeah.
co-host. All right. So, all right. So,
Let's see if it works.
yeah.
All right, can you see it?
Yeah. Yep.
Okay. My name's Bruce Eddieburn, and I'm not your typical graduate student coming back after retiring. So I'm actually a senior citizen now. But our project was to look at repurposing oil and gas wells to see if we can generate geothermal energy, after they're done producing oil, basically, oil or gas. So basically, the background on this is in the US, just the US, we've been drilling oil and gas wells for about 100 years. And once a well's reached its end of life, we have already a pre-drilled hole with a casing that's basically hot at the bottom and cold at the top, right? So maybe we can generate some energy from that situation. So each well, these are going to be low, let's say low yield producers, but there's a lot of them. So together it may add up to something. And it will definitely take smart grid technology to be able to, for all these small producers to push into the grid. Okay. So first thing we looked at is, what's the resource out there? And right now, there's basically 7 active regions where they're oil and gas drilling. And it took a little bit of work. We went through and we found out kind of what the average well is for each of these regions, right? So you have the Balkan and so forth. And generally it worked out to where the Anadarko, Pennsylvania area, this area here, has some very deep wells and it's pretty hot at the bottom. Similar for the Eagle Ford here and the Haynesville. And these actually have, let's say, good proximity to places like Dallas. This is fairly close to Houston. So the Anadarko is kind of in the middle of nowhere, but then again, we're not producing that much. So we'll take a look at this a little bit here. Just to give you an idea, that's Texas. And they've given basically a geocline. So the hotter areas are in here, up in here, here. So that'd be your Anadarko region, that'd be your Haynesville, and down there would be your Eagle Ford. And you'll see a lot of, they've color coded it here. So you're not after all these black dots. They're not very, let's say they're not very hot, not very deep. Up in here. So basically here's where our best resource is, here and up in here. Okay. Every year they're drilling about 20,000 wells. And in the last, let's say 100 years, there's 2 million holes in the ground for possible. So not too bad. There's plenty of resource out there. It's just a way of making it pay, right? So, and that 2 million number is probably a good number to remember. Okay. All right. So we looked at some particular clusters, and this is in Zapata County, and that's in the Eagle Ford. And you have, let's say, a cluster of wells. Each one of those is producing is one, it's very deep because what you're doing for the heat transfer equation is it's a function of the surface area, right? So if you have a very deep well, when you, let's say, pi DH that's a larger number. And when the temperature gradient's bigger, that helps you too. That's a linear relationship. So if you go twice as deep, you got twice as much surface area of the hot part of the pipe, your yield will be double, basically. So you want very deep and hot. And so let's go down here a little bit. So, and we also looked at Reeves County. It's a good average county with a lot of, sorry, I've got a cat in here. Okay, it's a very prolific county. It has about 1,300 wells drilled, and they're look like about 120 degrees downhole temperature is a good average, and about 5,000 feet. So we decided to kind of model that to find out what we can expect, right? So when we go to the resource, it's a function that heat transfer from Earth isn't very good. So you get about 5 watts. This is, I guess, from a geological paper. You get about 5 watts per meter per degree C. So if you have 1 meter of surface area and 10 degrees difference in temperature between what's receiving the heat and what's giving off the heat, then you get about 50 watts. Okay, so let's talk about what a well is. It's not just a hole in the ground. What you have is an outer casing, usually anywhere from 5 to 11 inches that goes all the way to the bottom. That's usually, I don't know, 5 to 15,000 feet. And then inside that casing is usually a 2 or 3 inch tubular. And that's what's actually transmitting the oil and gas to the surface. So that extends beyond the casing. They put a bunch of holes in it in, let's say, fluid producing material, strata. That flows up the flow line. About here's where the casing starts. When they take these out of service, what they do is they cut it there and they cement. And all of that is cemented away. And what you're left with is basically, I don't know, anywhere from 5 to 9,000 feet of 5-inch casing. Could be 7, could be 11, but 5's popular. 5.5 is popular. With an inner tube or a straw that's a 2-inch straw. And that little space between the two is called the annulus. Okay, so because this stretches a couple of miles and you don't want wells all hickledy-pickledy over the real estate, what they'll do is they'll group them together. So 18 seems to be a popular number, and I don't know why. So, but it's good for us because it gives us kind of a central point. So you could convert 18 wells and have one connection to the grid, right? So the one thing these sites don't have is usually access to water. Certainly not water for cooling or being able, or bodies of water you can discharge into. Let's get down a little bit. So we came up with some kind of rules for our conversion. We're going to use as much of the existing materials as possible. It has to be easy to maintain, low O&M cost, not require water resources, and it needs to be fully enclosed. And the other thing is, because these wells, they're owned by whoever drilled them, right? And it's let's say they're reticent to hand it over to somebody else because they know if XYZ small company goes there and causes some catastrophe, it's going to come back to them as the person that drilled the original hole, right? Because they're deep pockets. So needs to be attractive for them. Okay. So since it's fully enclosed, in the past, they generally used water for cooling. Water is a medium. Coal plants use steam and so forth. Well, there's a latent heat of evaporation for water. It's 2250 kilojoules per kilogram. Well, that represents a loss to us, right? So we're going to heat at the bottom, vaporize, and then recondense at the top. So that's a loss, right? What we're making our money on is the superheat. So if we use something like hexane as actually a lower boiling point to give us a larger delta between the earth temperature and our boiling point, one is we get more yield, more heat flow into the material. But we only have 365 kilojoules, so about 1/8, 1/7 the loss from just the heating and cooling portion of the cycle. So kind of the first thing we looked at was a system where basically we'll start here. We're going to send hexane down there, down to the bottom of the well through the tubular, and it'll come back, it'll boil and come back up through the annulus, drive the generator, be recondensed and pumped back down in the hole like that. Okay, so looks okay. You might make some money here, but it's got the moving part, which is this pump. And then we looked at, okay, well, if you put the condenser at the top and just let it drip, rather than needing a pump to give you head to drive it down, you just put a pressure control valve down the annulus, and you'll build up a column of hexane here, and it'll release it back down. So you can get rid of one part. Okay. The third thing we looked at was very low yield, but easy. Basically, you're going to insulate the middle section of the well. You'll allow the hexane to first flow down here, it boils, comes up this pipe, and recondenses at the top. So it's just doing reflux. And you put a generator in this pipe operating off this head. Seems pretty nice. You only have, quote, one moving part. So from the surface, it's pretty benign. You got a couple of wires coming out. It's doing its reflux 24/7. It would be low yield, but then again, let's say low cost for conversion and very low O&M cost. And the last one is this. And this is actually done commercially. We contacted a company, this company, Stella Energy, and proposed our same 5,000 foot, 5.5 inch casing, 5,000 foot well, right? And they said that basically they had some similar projects in Alberta, Canada, and you can get about 100 kilowatt out of that. And if you do some well intervention to add some heat transfer fluid to help the heat flow from the rocks to the casing, you can get up to 200 kilowatts. So, and that uses what they call a binary organic racing cycle. So basically what you're doing there is you'll take, let's say this valve is actually connected to the tubular, and this one is connected to the annulus. So they're taking cold fluid, letting it flow all the way down to the bottom in the annulus, getting hotter. And then when it gets to the bottom, it comes up the tubular in the middle through this valve and does its thing. And what its thing is, 2 heat exchangers and 2 circuits. So the first one, the hot fluid goes into this heat exchanger, adds superheat, comes here, adds preheat, and then goes back down. The second circuit, reading a fair number of articles on this, the popular one is isobutane. You got liquid isobutane coming out of your condenser, comes through here, gets heated first through the, let's say, partially cooled fluid that's going to the well, and then gets superheat here where the well fluid's hottest, drives a turbine and makes electricity for you. So you actually have 2 fluid circuits. One's the well, and that never boils or anything. You always keep that in the fluid state. So it's probably, for our case, going to be hot oil. So I just explained that. It uses 2 circuits. One circuit collects the heat from the well while taking cold fluid and sending that down the well annulus where it's heated. That's that cycle. And that one heats the second medium. Okay. And going off our well in Reeves County, we get about 100 kilowatts. 200 if we do well intervention, and let's say up the transfer of heat from the rock. So if we took a 18 well site, 100 kilowatt each, and we say, oh, look, we're going to get, an availability of about 90%, right? Because this isn't dependent on the wind. It's not dependent on day or night. It's base load power, right? And according to the energy information people, from average US cost is 13.72 cents per kilowatt hour for home use. You get about 2 million a year. So yeah, it's not huge. And I guess the conclusions are, abandoned oil wells can produce electrical power. The power is not dependent on wind or time of day. So it's good to add base load to, let's say, your overall portfolio of renewables. It's probably good for, right now, there's isolated communities. This may be their best option, especially if you get, let's say, rural communities, or there's some up in Canada where maybe they're not grid connected and they're using diesel right now or some other form to go ahead and find some well sites in their area and get some power.
Okay, and, Bruce, I think you need to wrap up.
Okay, I'm done. So
yeah, okay,
there you go.
All right. Yeah. Wow, very interesting. I honestly, this some companies in Grand Junction in Colorado, they
Yeah.
have similar, but they use regular geothermal volcanic kind of activities rather than in your case, you got already set up all the pipe and everything there. So maybe the capital cost is a lot lower in your case because you are using abandoned wells. I wonder if you consider, applying for DOE SBIR. Like first stage, first phase, you got a 200K. Yeah, you got a
Yeah.
proof of concept, and then you can, if they like what you did and they give you, I think second stage for 2 years, that will
Yeah.
be $1 million. And then, if they like it, and at the end of 2 years, you go on for commercializations. So, that's the process, how to, if you have the entrepreneurship spirit, and
Yeah.
and you got
Well,
plenty of time. So,
yeah, I've got plenty of time.
yeah,
There's actually a little bit of a pot of money out there too.
yeah,
Um, the abandonment cost when they drill a well, they have to set aside money for abandonment cost, and
yeah,
that's about 24,000 a well. So for an 18 well site, you got about 400,000 just sitting there. And if you get the government to release that money to you because you're not quote abandoning it,
right.
you might be able to harness that. And the larger oil companies are trying to, let's say, polish their energy or their image.
So
So
Bruce, you have a team, right? Why don't you why didn't you get together with a team, and look at DOE website specifically for SBIR, and it doesn't hurt to try. And if you are the first time, there will be a kind of counselor there available for you for free, which basically kind of coaching you how to write the good proposals, and you know you should try. Why not? If
yeah,
it
I
is,
may.
yeah, if it is not for you, maybe for your team members, who knows, you just become like sort of board members, and if you can work as a team, why not?
It'd be good. I'm
Yeah.
I'm thinking about doing. I'm finishing up. This is my last semester for my master's, and I'm thinking about a PhD.
Oh,
So
okay. Well, that's even better. That's even
there you
better.
go.
Yeah, send me an email, then I might get you. I might be able to find someone at NREL who might be interested. Who knows? But
Okay, that'd be
so
cool.
yeah. All right. So the next one will be Tom. Thomas is there. Hello. Hello. Is Thomas Orison there? Who is the next one? Thomas, are you there? I think you need to unmute yourself. Yeah, I think you stop
Hey,
sharing.
is this working?
Yes.
Yeah, sorry, it was registering the wrong microphone for it.
Okay. All right. So could you stop sharing, please, Bruce? You end your sharing, and I will assign Thomas to be my co-host. Next one. Let me see where. Oh, there it is. Okay. You are co-host now.
All right. So share screen. And if I do, is
Yeah.
displaying the
Got it.
awesome, perfect. So our project hinged on looking at piezoelectric and piezo-induced power systems and how to potentially implement them and help subsidize a little bit of the energy cost of large scale grids.
Oh.
You'll see throughout this presentation that we go into what is piezoelectric and generator, how do we approach grid integration with it, how is it produced, and then a couple of sites that we selected, how would our system actually operate with them. This very first slide is a wall of text. The biggest takeaways from it is why did we end up choosing piezoelectrics? And you'll see for all of the other renewable sources, solar, hydro, wind, geothermal, all of those require some sort of geographical benefit. So solar, you need to have a lot of presence of sunlight throughout the year. You don't want to have an area that's covered by clouds for the majority of the time, or have it in one of the Arctic places where you have like 6 month long nights. Hydro, you need water. Wind, you need places with good wind flow. And then on top of that, they have a very high footprint as far as room that it takes up. Piezo, on the other hand, are systems that don't really require any inherent geographical locations. Piezoelectronics are essentially devices that take mechanical stress and transmit it into electrical energy, which is the main draw for this. So we can put it on sidewalks, and the primary use that they are implemented in right now is to act alongside other energy sources. So they're often small devices operating at high frequencies, so it generates a lot of extra residual power to help mitigate the cost of, let's say, wind turbines, because as they go, they have a lot of vibration going on, and if you can take a little bit extra energy and cut off the cost of it, is pretty nice. Some of the problems that you might see come up with this is producing piezoelectronics. The cost of it can get pretty high. And then based on how you are setting it up, do you want it to be fully integrated into a grid system, or do you want it to have support for just a couple individual elements that are separate from the grid? We'll talk about those a little bit more, but very briefly, piezoelectricity, conversion of mechanical stress into electricity. There are three primary approaches to this as far as materials are concerned. The very first one and biggest one that we are actually going to be looking at throughout this presentation is ceramic materials. Those are a little bit more well known throughout the piezo industry and have a lot more properties defined for different materials. There are also simple crystals that have piezoelectric properties, and then nanomaterials, but I didn't really delve into the nano side because that requires a lot more fabrication going into it. And as far as looking at the actual values going for it, we have several different things. Biggest one, or relevant ones, are denoted by a D, and then you'll have two subscripts following. And these subscripts can range from 1 to 6, and they are generally the direction applied to it. So if you have 1 through 3, looking at a device, you have our general XYZ axis, and 1 through 3 denotes along which of those axes, and then 4, 5, 6 are shear forces, so angles angled between two of those fields for each of them. And how they typically generally work is you apply stress to the thing, piezoelectric material compresses and then induces a voltage output from the two. Another way of thinking about it is like a variable capacitor of sorts, but not entirely. Other key features for it is we have permittivity, and that just goes into affecting how much of this mechanical energy can actually be converted into an electrical output. Talking about these ceramics and crystals, these are just a few of the ones that are known, and each of them have their different constants listed, very useful in determining how they actually work. The most common ceramic, and actually the one that we are considering for this entire project, is lead zirconate titanate. I may have butchered the pronunciation there, but it is the most common and easily accessible of all of the ceramics. And if you want to look at it in electrical capacity, you can view it as you have your alternating current generator, Each piece has their own inherent capacitance and a little bit of resistance analogous to it. But we have it. You apply the force to the piezoelectric ceramic, outputs that voltage to whatever system you have set on up. One little infringement on it, not infringement, but one small drawback to it is currently they are very lossy. You can see most piezo systems expect to see roughly 63% loss of power from mechanical input to electrical, which is a pretty large margin. And then also for setting up the system, this is a lot of headway into the beginning portions of it, but you need to consider how is your ceramic shaped? How is it mounted? Or how are you getting that stress induction to generate power? And over on the right, we have a couple different mounting methods because you want to say, hey, if we compress it, how far is it going to compress? Because the distance that it moves determines how much of a power output it has. And most common between all of them is a bimorph element, where you just have your ceramic coming straight on through, and it's essentially flat, supported completely above and below the system. Generally, on the bottom left, we have a little bit of a display as far as the output power for meters per meter on it. You can see the expected output is relatively low, and that's because we are dealing with very small systems. But the main reason why this caught our eye is if you have a lot of really small systems in series and it can cover a large area, that can help generate a very, very large amount of energy over time if it is consistent. I believe this is the actual proper pronunciation of the system that we were talking about using for ceramics as lead zirconate titanate. Another thing you might notice with each of these ceramics, most common element in all of them is lead, which might lead to a little bit of environmental impact concern, but we'll address that in a little bit. Continuing on this slide, don't really expect to go over all of the constants used for it, but on the right, we have a little bit more in-depth on each of the different mounting types and how much power it can output for it. For our system, we're ending up using the simply supported bending unit, where we'll have two focal points lining ceramics as we lay them on out. So just so that y'all know, this is the setup that is being talked about in this presentation. Now, one big thing that we ended up finding out while making or modeling the system is that the dimensionality of our system matters a lot. As you can see, if we have just a 3-inch by 3-inch system, the third term is the thickness, because that's something we can't really change with the piezoelectrics. You want to make sure that it has charge going on through. You'll see that it requires 20 times less of a distance change in order to induce the same amount of voltage. I realize we are a little bit low on time, so I will fast forward on through this. And one big concern that we kept running into is the cost of this system. So what if instead of having purely piezoelectric ceramics to be considered, what if we had instead piezo-induced systems where we have mechanical stress, let's say foot coming down onto tile, and you have that downward pressure to potentially inspire the generation of a system we've already looked at, such as like oscillated water column, point absorber, or a wind turbine. A large portion of this project I spent looking into trying to model a Wells turbine for this, where if you have the downward pressure affecting a chamber, and that chamber expels a bunch of air past a Wells turbine to get it to spin, and then on the release of pressure, the chamber would rise up, sucking in wind to keep the Wells turbine moving. which is this general approach right here. It would still generate a very, very low amount of force, but I needed to get more simulations done for it and actually ran out of time and was unable to finish the simulation results for this, which is listed in future works as far as what we need to work on more. But there are two commercialized approaches to this presently. One is PaveGen, which is a piezo-induced approach, and you can see our specifications right here. They're using more of a induction generator for the press and release. And then we also have energy floors, which is listed up here. I couldn't find any specifications on the method of which they are generating energy, but I believe it to be more of a crystal type application for it. Both are relatively cheap. PaveGen actually is in use in, I believe, 15 locations around the world and help generate setup around the area as fairly well recognized. And Energy Floors is more for entertainment type applications, and you buy them and they pretty much generate power for their own system and surrounding systems that are not permanently connected to a grid. As far as grid generation and the nitty-gritty of what we actually wanted to do, we have some values for what our system would have, and our system is essentially 1 square foot of 16 different piezo models using the 3-inch by 3-inch setup detailed earlier. And you can see if we select 3 different sites, such as Times Square in New York City, Atlanta International Airport, and Shibuya Station in Tokyo, we can generate 30 kilowatts, 15 kilowatts, and 189 kilowatts a day for each of those systems. If we want to go per month, if we have a 10 square foot setup, it can get pretty high up there, which is really good for general power generation as far as kilowatt hours. And you'll see right here, we have the average home daily consumes 26 to 33 kilowatt hours a day. And this would actually help, if we have a large enough area, offset that cost for the entire year. As far as integrating it to a grid, the best setup we could come up with is a battery energy storage system, where we have our piezoelectric ceramics or tiles. You walk on them, they generate the power that goes into a battery system for helping out in system load or powering whatever devices are near on by. And since piezoelectronics do provide a very small amount over a large sorry, I need to take a little second right now because I've been talking really fast. But piezo ceramics do generally provide a lot smaller voltage than most other systems. We want it to be in conjuncture with another system that is utilizing the batteries. So most of these would be in combination with PV systems or other sources that are powering or helping supplement the cost of the grid nearby. As far as grid protection, I didn't really work too much on the grid protection stuff. That came from, I believe, Hayden Will, and they know a lot more about this section. But we do need to make sure that the battery is safe to use and doesn't get overloaded by any outside sources, or if we have any fault currents running on through, we don't want it to mess up our system or just blow our entire piezo setup. So this is a potential approach to it. As far as environmental impact, is probably best if we do end up using ceramics to either encase it in a material to help mitigate the force on it and make sure that it doesn't crack or break, and potentially have a drain catch underneath to prevent the leakage of lead into the soil of the area and similar effects. As far as site selection, I mentioned Times Square, New York, Atlanta International Airport, and Shibuya. The main reason for these is they are high pedestrian traffic areas, seeing roughly about 360,000, 200,000, 2.4 million people respectively. And the main impetus for us going on this research topic is a paper in 2008 where we had Kohei Hayazuma pretty much do the same exact thing and try and power part of Shibuya train station's terminal doors via a piezo pad, which actually ended up working for a 20-day trial period that they had. Cost analysis, this is where we get into the damage of the part, because piezoelectronics are a lot harder to produce than any kind of piezo-induced system, because you need to dope the ceramics, you need to measure them, test them, make sure that they do have this properties that you're saying they do, so you can estimate how much it has. And the main reference material that we're using is the T110 A4NO 2929 piezo plate. And for that, it comes out to roughly 2.3 thousand per square foot. Meanwhile, Pavgen is about 351 per square foot. The helping factor here, though, is at its conception, Pavgen, their approach, each tile ended up costing about $7,600 to produce, and now they're down to $350. So if a lot more research goes into potential layouts and the production methods of ceramics, we might also be able to achieve a similar result and up the production cost, production value of it. But as it currently stands for each of those sites, using the energy price as of January this year, it would take the Times Square one roughly 28 years to pay off and get a return on investment. Atlanta 78, but Shibuya would take only 4 years to do that. Another cost that was not expressed in the return on investment is the battery energy storage system, which is approximated to be about $45,000 to $60,000. Future work, we can work on trying to look at the piezo-induced systems, how much would they produce, and all that. And try also making production of piezo materials a little bit more efficient. Conclusion, it is independent of geographical elements, and it is a truly passive form of generating energy, but it is heavily dependent upon human behavior of the area. So you need it in high foot traffic areas. And currently, it is inefficient to actually implement cost-wise. Do we have any questions?
Any question, guys? It seems to be very interesting. At this point, it's kind of a little bit expensive, but
Yeah.
you know, a lot of government funding is made available for this kind of work, you know, where not too many people is interested in doing this. And you know, again, you know, like Bruce, you know, I would encourage you, I'll send you the link to DOE SBIR, and you know, it doesn't hurt to try. You know, the worst case is that they will reject your proposal. That's it, right? You don't lose money over it anyway. All right. So do you have any questions, guys? So if not, then I'll close this presentations, and thank you very much for attending. And please remember, you fill up your score sheet and send you know, your spreadsheet to me once everybody else is done. So, all right, thank you very much. Bye-bye now. I'll see you on Wednesday.
Thank you.
Yeah, bye-bye.